Hi, Diana.
Hello.
Oops, clicked on the wrong thing. There. Turn my volume up a little bit. So how are you doing this evening?
So far, so good.
Okay. Hopefully I'll be able to help you. I'm recognizing some stuff that I'm not real strong on statistics. And I know that the IB program gets into statistics pretty good. I know that median means middle, mean means average, and mode means most common. So
Right.
you have found the median number of hours of sleep that everybody gets, right?
That's not the question that I'm having trouble with. Number 9, the one that I circled, is my main problem.
Good. I was hoping that was the case because I hope you understand this stuff. You probably understand this stuff better than I do.
Yeah, that part is not a problem for me.
Okay. I think I can do 9. Okay. Let's figure out what the inverse is. How do we do that? What's the standard way to figure out an inverse?
Of a log?
Well, you can do it with logs. The standard way of figuring out an inverse to a function is to switch the variables and solve for y.
Oh.
Okay, so if I switch the variables,
Wait, that gives... Oh! That's what okay, I was thinking y prime. That makes more sense now.
okay, well, I think that's what they mean by f to the minus 1 is inverse, as opposed
Right.
opposed to f prime, yeah. Sometimes it's easy to get them confused. So how do I solve this for y?
You could turn it in, like, switch it away from a log function.
Well, we can do that, but
Okay.
there's a little bit of a better way to do it. Let me show you. First of all, let's isolate log base 2 of y by dividing both sides by k. Now, if I want to solve this for y,
I mean, couldn't you turn it into an exponential function? So that way it's y equals 2 to x over k?
yes. The other way to look at that is let's exponentiate both sides to base 2. And I'm allowed to do that. It's a pretty cool technique that you want to learn about in math. In other words, if I have x equals 2y, then I can say that 2 to the x equals 2 to the 2y. Or I can say that e to the x equals e to the 2y. In other words, I can put whatever I want underneath those. And that's what I did here. I exponentiated each one of them from 2 to the base, to that side of the function. And notice what that leaves on the right side. When I take 2 to the log base 2 of y, I get y. And on the left side, I get this. And that's what you wanted to do in the first place. Right?
Oh, so it works either way.
It works exactly the same way. But this other technique comes in handy sometimes on different kinds of problems, and that's why I wanted to point it out.
Oh, I'm sure it will come up when I take AP Calculus.
Yeah, it definitely will, because there's a couple of types of math problems where you have to solve them by doing that. Okay, so I've got y equals 2 to the x over k. And this y is f inverse of x. So if that's equal to 2 to the x over k, and they're saying that f inverse of 1 equals 8.
So 8 equals 2, 1 over k.
Yes. 8 equals 2 to the 1 over k. What would k be equal to? If
3?
not quite,
No.
but close.
It'd be the other way.
1/3.
1 over 1/3.
In other words, we know that we know that 1 over k has to be equal to 3, correct?
Right.
So k equals 1/3. 2 to the 1/3, excuse me, 2 to the 1
to the third.
1/3 power
1/3.
equals 8, because that's the same as 2 to the 3rd power. Okay? So we've solved for k. So now we know what the original, or what the inverse function actually is. It's f inverse of x equals 2 to the x, to 2 to the 3x. Really?
Yeah.
Okay. And part B, find f inverse of 2/3.
Wouldn't that just be 4?
Can you, is that not visible to you? I wonder. Is that 4?
Oh, I see it now.
Okay, well, I wasn't sure if it maybe wasn't visible to you.
No, I was just
Occasionally
there's
parts of my screen that I've discovered students don't see if it's in a certain area of my screen. So I didn't know if that was one of those cases. All right.
No, I could see it just fine.
Okay.
All right, the next problem, question number 11.
All right. This looks like it would be a log problem, but it's not. It's easier than a log problem.
Could you possibly keep it of the same base? I just thought of this just now. Like, since I know 27 is 3 to the 3rd.
Exactly. In other words,
and then 9 is 3 squared.
Right. And
in other words, it's essentially 3 4 to the x?
It's a common exponential base. When you have problems like this, if you can find a common exponential base, then you can solve them without logarithms. Because I can write this. I can write 9 as 3 squared to the 2x. I can write 27 as 3 cubed. And the parentheses are very important here.
Right.
Now, using the rules of exponents.
So it would be 3 to the 4x equals 3 times 3 minus 3x?
Like that. And now you can equate exponents. In other words, if you have the same base to one exponent equals the same base to a different exponent, then the exponents have to be equal. This is kind of the reverse of what I was talking about just a minute ago. In other words, if I started with this, then I could say, well, any number to the 4x power is equal to that same number to this power. You know what I'm saying?
Right.
Okay. So this solves relatively easy. You have 7x equals 3, x equals 3/7.
Right.
Okay.
It works.
Now, typically, if these were numbers other than perfect or common exponential bases, Let's say this was 26.
Oh dear.
Now it's not so easy to solve with that technique. But it's easy enough to solve. We just take the log of both sides. I always use natural log.
Right, since natural log is just log base 10, right?
It's log base e. Common log
right,
is
e.
log base 10. I could use either one here. I'm partial to natural log because it's such an integral part of calculus. Once you get calculus, you don't hardly use any other base but natural log. But once I've done this, this becomes 2x natural log of 9 equals 1 minus x. In other words, by taking the log of both sides, I'm able to bring that variable exponent down onto the equation line, getting it out of the exponent. We don't have algebraic ways to solve for exponent variables. But now I can solve it. This is just a number. That's just a number. I got one equation and one unknown, easy enough to solve.
Right.
I mean, maybe not that easy. You have to distribute, and some people might have a little difficulty with this, but you won't have difficulty with this as long as you always recognize that these are just numbers. It's kind of like the sine of 30 degrees is just a number. It's not any kind of strange function or anything. In other words, if I substitute the number 3 for that, then I have 2x times 3 equals 1 minus x times, let's call that 7. Now it's real easy to solve.
Right.
Well, you solve it the same way by distributing this natural log of 26 to both of these terms and then gathering all the terms with x on them on one side, all the terms with numbers on the others, and just use your straight algebraic solution. The moment you take the natural log of both sides here, you now have an algebraic equation. When I start with this, that's not an algebraic equation. I don't have any algebra that'll solve that. If I didn't have logarithms, I couldn't solve this. Now, when it's 27, now we have a common exponential base and I can solve it. But the moment you lose the common, and usually you don't have a common exponential base. I mean, you know, they have to be creative to give you problems that have common exponential bases. Typically, you don't have common exponential bases, and you have to solve these problems by taking the logs of both sides. And it doesn't matter whether you use common log or natural log. And the reason it doesn't matter is because of this. If I say the natural log of that, that's exactly the same ratio as the common log. That's exactly the same ratio as the log base 17. All these logs ratios are the same, no matter what the base is. Which means that when I go to solve this problem, whether I use common log or natural log doesn't matter, because my answer is going to be a ratio of log functions. You don't want to use log base 17 because your calculator doesn't have a log base 17 key on it. It only has common log and natural log. So those two are usually the ones you want to use when you're solving an exponential equation.
Okay.
Okay.
Oh, could you explain to me when to use the discriminant?
Yeah. Why does this thing have its own name, the discriminant? Because if that discriminant is a positive number, we're going to have two real solutions to our quadratic. If it's a negative number, we're going to have two imaginary solutions. And if it's exactly equal to 0, we're going to have one real solution. So, if I give you a quadratic, and I say solve that, it might be useful for you to know whether it has real solutions or not. In other words, if it has nothing but imaginary solutions, we know it's going to be a parabola that doesn't intersect the x-axis. We know that if it has real solutions, it's going to be a parabola that intersects the x-axis in two spots. And if this thing's equal exactly to 0, it's only going to have one solution, and it's going to intersect the x-axis in one place only. So that's why the discriminant is an important value, is it gives you a preliminary test as to what kind of solutions you're looking at for the quadratic. And sometimes, depending on the nature of the problem, if you know that you're only going to have imaginary solutions, you don't need to go any further. You know, if you're trying to find the dimensions of a box and you say, you look at the discriminant and you realize that I'm only got imaginary solutions here, there are no solutions to my measurements of this box. So you're done. So a lot of times you can advance towards the ultimate solution by starting by looking at the discriminant. In this case, with this particular function, b squared would be 1 minus 4 times 1 times 10. Well, that's negative 39. Because that's negative, I know that this does not have any real solutions. That can be useful to know without solving. In other words, without going through the entire quadratic formula to come up with the exact solutions, you might realize that, well, if the discriminant is negative, I'm done with the problem. In other words, if they gave you this function, x squared minus x plus 10, and they said, where does that intersect the x-axis? You don't need to go through this whole thing. You can just analyze the discriminant, realize that it's negative, you have only imaginary solutions, this thing doesn't intersect the x-axis. It also opens up, so I know it would look something like that. But I could immediately say it doesn't have any zeros.
Huh. Okay.
Now that doesn't seem to go with anything on this page. Is that just something different?
Yes.
Okay. And this page, you use the binomial distribution to do this?
Yes.
And also this?
Yes.
Okay. Well, that takes care of everything on that page then. You got anything else?
No, I do not. Since everything else in this packet was simple.
Okay. Okay. This problem number 11, you will see this kind of a problem on the SAT test and the ACT test.
Okay. I just kind of
you don't need to know logs for either one of those tests.
Right.
But this is not a log problem. This is a common exponential base problem. And these can present themselves in a variety of ways. One that will confuse people a little bit is if I say this, what's the common exponential base? Not 4.
2.
Exactly. In other words, it's not the common factor. It's
Right.
a common I need to be able to write both of these numbers in the same base. So this would be 2 squared and this would be 2 cubed, and then I would go about my business applying the rules of exponents and stuff. But a lot of people would make the mistake of making the 8 look like 2 times 4, which seems to be a reasonable thing to do, but you can't get anywhere now. That doesn't help. I can't then apply the rules of exponents and equate the exponents. So it's only if I have a common exponential base that I can do it. I suppose if this were a 3, no, I'd have to use logs. There's just no way to solve this without logs. Take the natural log of both sides, or the common log, bring the exponent down there, and now proceed to solve it using algebra. All right. Well, if you don't have any other questions, I can certainly let you go.
Yeah, that's all I have.
Okay.
And next week, I don't think I'll need it since
because you have spring break next.
Yes, I do have spring break.
Okay, so I'm probably going to run into that with a lot of my students, huh? Let me cancel next week's while we're talking about it, and I will talk to you 2 weeks from now.
All right.
Okay?
Well, thank you.
All right, Diana. Have a good couple weeks. Enjoy your spring break.
All right.
Bye.
Thank you. You too.
Bye.